Something about modern freight locomotives does not add up. Today's engines often have fewer cylinders than their ancestors, yet their radiators have exploded in size, jutting out as massive metal wings instead of the old flush panels. This is not cosmetic. It is a clue to a deeper engineering paradox. If the engine is smaller, why does it need so much more cooling? To solve this, we will follow the invisible trail of waste heat, horsepower, and policy pressure that made larger radiators not just inevitable, but essential, and discover what is truly at stake every time a train powers across the continent. Every time a locomotive burns diesel fuel, the laws of physics take over. Only a fraction of that fuel becomes useful work, turning the wheels and pulling thousands of tons across the rails. The rest, nearly 2/3, transforms instantly into waste heat. In practical terms, for every 10 gallons of diesel poured into the tank, about 7 gallons worth of energy must be dumped as heat, mostly through the radiator and some through the exhaust. This is not a design flaw or a missed opportunity. It is an unavoidable outcome of how heat engines work. Even the most advanced locomotive diesels, running at their best, top out around 35% thermal efficiency. That means roughly 65% of the energy locked in each gallon of fuel is destined to become heat that needs to be rejected just to keep the engine from destroying itself. This heat budget is enormous. A mid-century freight engine running at full power would push out over 1 megawatt of waste heat, enough to heat several city blocks. See, modern engines, despite their technological advances, still face the same basic math. No matter how efficiently the engine runs, the majority of the fuel's energy will always exit as heat. The radiator's job is to move this invisible torrent safely out of the machine, around the clock, in every season and climate. The size of the radiator, then, is not an aesthetic choice. It is a direct physical response to the relentless arithmetic of energy conservation. As horsepower climbs, the heat to be managed climbs with it. This is the starting point for understanding why, as engines evolved, their radiators grew from modest panels into the massive wings seen today. A side-by-side look at horsepower tells the story in numbers. In the 1960s, a typical freight locomotive like the GE U25B or EMD GPE delivered about 2,500 horsepower, roughly 1.2 megawatts of mechanical output. Fast forward to today's GE Evolution series or Tier 4 models, and that figure jumps to 4,400 horsepower, about 2.0 megawatts. This is not just a bigger engine under the hood, it is a leap in the amount of energy being processed every second. The laws of physics do not cut any slack. Even as thermal efficiency improves slightly, the total waste heat grows almost in lockstep with horsepower. For a 2,500 horsepower unit, the radiator and cooling system had to handle over 1 megawatt of heat, already a daunting task. But at 4,400 horsepower, the heat rejection requirement soars to nearly 2 megawatts. That is a 70% increase in the sheer volume of heat that must be moved out of the engine bay and into the atmosphere, continuously, mile after mile. Manufacturers could not simply scale up the old cooling systems. The jump in power meant the radiator surface area had to expand dramatically. What was once a compact, flush-mounted panel became a sprawling wing hanging off the rear of the locomotive. This physical transformation was not a matter of style or preference. It was the only way to keep up with the relentless heat generated by modern, high-powered engines. As horsepower climbed, so did the demand for cooling muscle, making oversized radiators an unavoidable feature of the modern freight locomotive. Modern freight locomotives no longer rely on a single coolant circuit to manage their enormous heat load. Instead, they split the job among 4 distinct thermal loops, each with its own unique demands. The main engine block loop still does the heaviest lifting, carrying away between 1,200 and 1,400 kilowatts of heat from from the cylinders, heads, and turbocharger housing. But that is just the start. The intercooler loop, dedicated to cooling the compressed air fed to the cylinders by the turbocharger, adds another 300 to 400 kilowatts. This lower temperature stream is essential for keeping intake air dense and combustion efficient, and it means a separate radiator section and airflow path must be carved out of the locomotive's rear wing. The introduction of exhaust gas recirculation, EGR, for Tier 4 emissions compliance brings a third major loop. Here, up to 250 kilowatts of heat must be extracted from exhaust gases before they are routed back into the engine to cut nitrogen oxide emissions. After treatment systems round out the quartet. Devices like diesel particulate filters and oxidation catalysts need to stay within a narrow temperature window to destroy soot and unburned hydrocarbons effectively. Their cooling loop adds another 100 to 150 kilowatts to the total burden. Stacked together, these four circuits demand the radiator system absorb and shed between 1,750 and 2,200 kilowatts of heat, nearly double what a 1960s locomotive faced. The result is a rear wing packed with separate cores, each sized for its particular loop, and each fighting for airflow. This is why the modern radiator is not just bigger, it is fundamentally more complex, with each new emissions or performance requirement carving out a new slice of the locomotive's cooling real estate. In 2015, the Environmental Protection Agency imposed Tier 4 standards that left no room for compromise. Locomotives now had to limit nitrogen oxide emissions to 1.3 grams per brake horsepower hour and particulate matter to 0.03 grams per brake horsepower hour. These were not abstract targets, they were binding and enforced at every step of production. The numbers forced a fundamental redesign, and manufacturers responded by lowering combustion temperatures, a move that required recirculating up to 30% of the engine's own exhaust back into the intake. This exhaust gas recirculation, called EGR, was effective at reducing nitrogen oxide emissions, but it created a relentless new heat burden. The EGR cooler alone added as much as 250 kilowatts to the system's thermal load, heat that could not be ignored whether the locomotive was hauling freight across the Rockies or idling in a switching yard. After-treatment systems brought their own complications. Diesel particulate filters and oxidation catalysts demanded precise temperature control. Too hot, and the catalyst degrades. Too cool, and emissions spike. Each device needed its own cooling loop, and each loop its own share of radiator surface. The Environmental Protection Agency's design guidance was explicit. For every 1,000 horsepower, at least 4.5 square meters of radiator area was required. For a 4,400 horsepower locomotive, that meant nearly 20 square meters of radiator core, double what was typical in the 1960s. Every extra fan, every added coolant channel was a direct answer to the law's demands. The cooling system expanded, not by choice, but by necessity, each new rule leaving a physical mark on the machine. The puzzle deepens when looking inside the engine itself. Modern freight locomotives like the GE Evo series run with just 12 cylinders compared to the 16 found in the classic FDL engines of the 1960s. Yet these newer engines push far more power through each cylinder. The secret lies in the numbers. The bore and stroke have both grown, reaching 250 millimeters and 280 millimeters in the GE Evo V12. Compared to 230 by 260 millimeters in the old FDL 16. That means each cylinder now displaces about 30% more volume, but it does not stop there. Cylinder pressures have jumped as well, with mean effective pressure rising from about 9 bar to 12 bar. Higher pressure means more energy and more heat packed into every combustion cycle. This concentration of power drives up the heat flux on cylinder walls from around 560 kilowatts per square meter in legacy engines to 820 kilowatts per square meter in the latest designs. That is a 45% increase in the rate at which heat must escape each cylinder, even though there are fewer cylinders overall. The result is a paradox. Shrinking cylinder count actually intensifies the cooling challenge, forcing thicker walls, more aggressive oil cooling, and ultimately much larger radiators to keep the thermal balance in check. The physical bulk of the radiator is a direct response to this invisible spike in per-cylinder heat. For railroad operators, the payoff of these oversized radiators shows up in the numbers that matter most: uptime, maintenance, and the bottom line. Since the rollout of Tier 4 locomotives, field data from Class 1 railroads shows a drop in engine overheat shutdowns by as much as 20% compared to older Tier 2 models. Fewer shutdowns translate directly into more miles between unscheduled stops, higher fleet availability, and fewer costly delays. On average, the mean time between failures for cooling systems has climbed from about 2,600 hours in legacy units to nearly 3,800 hours in the latest GEVO designs. That is a tangible reliability gain, even as the systems themselves have grown more complex. The economics are just as clear. Retrofitting yards to handle the extra clearance for radiator wings runs about $3.2 million per 100 locomotives, but annual fuel savings of roughly $1.1 million and emissions credits worth another $600,000 help balance the books. Maintenance hours per unit are up by about 10%, as crews now service dual blowers and 4 coolant loops, but this is offset by the reduction in emergency callouts and the improved predictability of scheduled maintenance. For the people running the trains, the larger radiators are not just a technical fix, they are a strategic investment, delivering steadier service and measurable savings year after year. Today, the oversized radiators are not excess, they are survival. As horsepower climbs and emissions rules tighten, hidden heat becomes the ultimate constraint on industrial power. Every massive radiator you see is a public reminder. Progress demands we tame not just fuel, but the relentless physics of waste heat. Thanks for watching.